7. Operating system structure. We know the operating system is composed of several components. Here we discuss the way that these components are interconnected and melded into a kernel. Simple structure. Many operating systems do not have well-defined structures. Frequently, such systems started as small, simple, and limited systems, and then grew beyond their original scope. MS-DOS is an example of such a system. It was originally designed and implemented by a few people who had no idea that it would become so popular. It was written to provide the most functionality in the least space, so it was not carefully divided into modules. In MS-DOS, the interfaces and levels of functionality are not well separated. For instance, application programs are able to access the basic I/O routines to write directly to the display and the disk drives. Such freedom leaves MS-DOS vulnerable to errant programs, causing entire system crashes when user programs fail. Of course, MS-DOS was also limited by the hardware of its era. Because the Intel 8088, for which it was written, provides no dual mode and no hardware protection. The designers of MS-DOS had no choice but to leave the base hardware accessible. Another example of limited structuring is the original Unix operating system. Like MS-DOS, Unix initially was limited by hardware functionality. It consists of two separate parts, the kernel and the system programs. The kernel is further separated into a series of interfaces and device drivers which have been added and expanded over the years as Unix has evolved. We can view the traditional Unix operating system as being layered to some extent, as shown in this figure. Everything below the system call interface and above the physical hardware is kernel. So you can see it has a large kernel. Okay? The kernel provides the file system, CPU scheduling, memory management, and other operating system functions through system calls. Taken in sum, this is an enormous amount of functionality to be combined into one level, the kernel. The monolithic structure has difficult to implement and maintain. It has a distinct performance advantage, however. There is very little overhead in the system call interface or in communication within the kernel. We still see evidence of this simple monolithic structure in the Unix, Linux, and Windows operating system. Second section, layered approach. With proper hardware support, operating system can be broken into pieces that are smaller and more appropriate than those allowed by the original MS-DOS and Unix system. The operating system can then retain much greater control over the computer and over the applications that make use of that computer. A system can be made modular in many ways. One method is the layered approach, in which the operating system is broken into a number of layers. The bottom layer, layer 0, is the hardware. The highest layer, layer N, is the user interface. So, such as this picture. The lowest layer is hardware. The highest layer is user interface. An operating system layer is an implementation of an abstract object made up of data and the operations that can manipulate those data. A typical operating system layer, say layer M, consists of data structure and a set of routines that can be invoked by higher level layer. Layer M in turn can invoke operations on lower level layers. The main advantage of the layered approach is simplicity of construction and debugging. The layers are selected so that each user functions and services of only lower level layers. This approach simplifies debugging and system verifications. The first layer can be debugged without any concern for the rest of the system, because by definition it uses only the basic hardware. Once the first layer is debugged, its correct functioning can be assumed while the second layer is debugged, and so on. If an error is found during the debugging of a particular layer, the error must be on the layer because the layers below it are already debugged. Thus, the design and implementation of the system are simplified. Each layer is implemented only with operations provided by lower level layers. A layer doesn't need to know how these operations are implemented. It needs to know only what these operations do. Hence, each layer hides the existence of certain data structures, operations, and hardware from higher level layers. The major difficulty with the layer approach involves appropriately defining the various layers, because a layer can use only lower level layers. Certain careful planning is necessary. The layered implementations is less efficient than other types. For instance, when a user program executes an I/O operation, it executes a system call that is trapped to the I/O layer, which calls the memory management layer, which in turn calls the CPU scheduling layer, which is then passed to the hardware. At each layer, the parameters may be modified, data may need to be passed, and so on. Each layer adds overhead to the system call. The net result is a system call that takes longer than does one on a non-layered system. 3-section microkernels. The microkernel moves this method structures the operating system by removing all non-essential components from the kernel and implements them as system and user-level programs. The result is a smaller kernel. There is little consensus regarding what services should remain in the kernel and which should be implemented in user space. Typically, however, microkernels provide many more precise and memory management in addition to a communication facility. So you can see, in microkernel, we only have memory management, CPU scheduling, inter-process communication, and hardware. So the main function of the microkernel is to provide communication between the client program and the various services that are also running in user space. Communication is provided through message passing, which was described. For example, if the client program wishes to access a file, it must interact with the file server. The client program and the service never interact directly. Rather, they communicate indirectly by exchanging messages with the microkernel. One benefit of the microkernel is that it makes extending the operating system easier. All new services are then added to user space and consequently do not require modification of the kernel. When the kernel does have to be modified, the changes tend to be fewer because the microkernel is a smaller kernel. The resulting operating system is easier to port from one hardware design to another. The microkernel also provides more security and reliability since most services are running as user rather than kernel. If a services fail, the rest of the operating system remains untouched. Some contemporary operating systems have used the microkernel approach, such as 264 Unix and Unix, etc. Modules. Perhaps the best current methodology for operating system design involves using loadable kernel modules. Here, the kernel has a set of core components and links in additional services via modules, either at boot time or during runtime. This type of design is common in modern implementations of Unix, such as Solaris, Linux, and Mac OS X, as well as Windows. The idea of design is for the kernel to provide core services while other services are implemented dynamically. As the kernel is running, linking services dynamically is preferable to adding new features directly to the kernel, which would require recompiling the kernel every time a change was made. Thus, for example, We might build CPU scheduling and memory management algorithm directly into the kernel and then add support for different file systems by way of loadable modules. The overall result resembles a layered system in that each kernel section has defined, protected interfaces, but it is more flexible than a layered system because any module can call any other module. The approach is also similar to the microkernel approach in that the primary module has only call functions and the knowledge of how to load and the communication with other modules. But it is more efficient because modules do not need to invoke message passing in order to communicate. The Solaris operating system structures shown in this figure is organized around a core kernel with 7 types of loadable kernel modules. Linux also uses loadable kernel modules, probably for supporting device drivers and file system. Such a design allows the kernel to provide core services, also allows certain features to be implemented dynamically. For example, device and bus drivers for specific hardware can be added to the kernel. Support for different file systems can be added as loadable modules.